I would like to thank the conference organizers for giving me the opportunity to speak and for putting on a fantastic conference. I've had a really great time, and I think many people I've talked to have as well. So with that, let's get right to it. So I'm going to be just giving you an update on the lensing reconstruction program from the South Pole Telescope. And in particular, I'm going to be highlighting the work of two people, actually the thesis work of both of these people. Yuki Omari, who led the first analysis that I'll be talking about with the SPT and SPT data, and Monica Makano, who is leading the second analysis that I'll be talking about with SPTpol data. And so this is the work of a large collaboration. This is the SPT collaboration at a recent collaboration meeting, so representing the work of many people. It's about, the core collaboration is somewhere around 40 to 50 people that it takes to really make all this happen. So I'm not going to spend much time at all on an introduction to lensing, since we've all been here all week and many people are already experts in this. But just for students or other people in the audience of one or two slides of background, lensing is just the fact that CMB photons travel from the last scattering surface to us to observe today. The travel paths are bent by this structure, and this the way that we describe this is a remapping. This causes a remapping of the apparent arrival position of these photons, and we can describe that as with the gravitational lensing potential phi. So this is an integrated gravitational lensing potential that we can use to describe CMB lensing. So this is the quantity. When we say phi reconstruction, we're making actually maps of this quantity. And then just one slide on why do we care about lensing. It should be obvious by now, but it allows us to probe the matter distribution over a broad range of redshifts, approximately z of 1/2 to 2. So we're getting a measurement of this large-scale structure. And one thing that's unique about lensing is it probes the mass. Rather than using light as a tracer, you're directly sensitive to the mass in the universe. And it's sensitive to both geometry and the growth of structure in the universe, and then as the many talks in this conference in particular have been talking about, we can use it to characterize and remove lensing beam modes and search for inflation. And so since I'm talking about reconstruction, I will be talking about a quadratic estimator. So these tools that Marius and some other people are talking about are really exciting, and we're all really interested to see work on them and see how they can work out. But the quadratic estimator so far has been extremely powerful and has allowed us to make the progress that we've made so far. So basically the one thing that I want to say is just the way this works is that in the quadratic estimator, you're looking at the correlation between, lensing introduces correlation between modes that was not there in the unlensed maps. So the way this estimator works is you're just simply measuring that off-diagonal correlation between two fields. When people say quadratic estimator, we're putting in maps of, two maps of CMB fields, looking at their correlation, and then basically taking a weighted sum of the off-diagonal elements of these two maps in order to reconstruct a map of the lensing potential. In this case, it's represented as in 2D harmonic space. But then, particularly for polarization, then you just simply put in T, E, or B maps into this formalism, and then can drive an estimator for each of these combinations. So the data set that I'll be working with is from the South Pole Telescope. We've already had some talks about this, but just as a reminder, there have been 3 cameras on the South Pole Telescope so far. The first camera was the SPT camera that was on from 2007 to 2012. Then we put on the SPTpol camera in 2012, adding polarization sensitivity, and Alessandro Mazzati presented results from that camera. And then just this past year, we put on the SPT3G camera, which increased the number of detectors by an order of magnitude, and Sasha presented on this yesterday. These are the surveys, so sort of the sky area, and for the experts in the field, some numbers of the depths that we've achieved. And so what we're reporting here, this is all data in the can. So there's the yellow region here is the 2500 square degree SPT region. Here showing the data from 90 gigahertz. You can see the temperature anisotropy fluctuations popping out there. Then in this small field here, this is the SPTpol deep field, this column. This is the 100 square degrees that Alessandro presented on yesterday. This cyan region here is a 500 square degree patch, the SPTpol patch, and by design this has exact overlap with the bicep Keck observation region. And then we've also during the summer observed a significant amount of sky, doubling our survey coverage. And so we're in the process of creating cluster catalogs from this data. There's a lot of interesting things that we hope to do with that. So all in all, we've observed around 5,000 square degrees with this instrument and continue to observe. Okay, so the first analysis is the SPT-SZ survey. So again, this is this yellow region that was observed with the temperature-sensitive camera between 2007 and 2012. For this analysis, we have combined Planck data, the Planck temperature maps, with the SPT-SZ maps. And so what you're seeing here, this is in LM space. This is a representation of the SPT noise. And so you can see that we measure out to the scales that are relevant for this lensing analysis really well. Our beam allows us to go to much smaller scales than this even. The Planck noise here, so they measure large angular scales very well, and then you can see the beam starting to kick in and increase the noise here at finer angular scales. And then we're just simply taking a inverse variance weighted combination of these two data sets. So this shows the relative weight of the two maps in LM space. So SPT is dominating up here, and then Planck is dominating down here. And this shows what this kind of looks like in simulated maps that have been run through simulated time stream mock observing analysis. So this is the input, the Planck maps. These rows are different Lmaxes, so Lmax of 2,000 versus 6,000. So Planck really gets these large angular scales really well, whereas SPT is less sensitive to those. But at the finer angular scales, Planck is totally noise dominated, less we filter it out, whereas SPT is picking this up. So the result of these two maps is a very deep, very complete map that covers the range of angular scales very completely. And so we apply a project estimator. A whole talk could be done about that process, and this is the resulting lensing map that we've observed. And so to kind of compare this map a little bit to the Planck maps, the SPT map here and the Planck map here. The Planck map measures the entire sky, but it's not as sensitive in any given patch of sky. And that's represented, what I'm showing here are the noise curves these are actually what are plotted with the bias terms. But you can think about these as plots of the noise in the map, okay? And so with the minimum variance estimator from Planck, we're just barely measuring a few modes of signal noise of 1. It's like, it looks similar here, although it's misleading because the theory spectra that are plotted are slightly different. So this map is indeed higher signal noise, and the map doesn't necessarily look like it. But you can also see that as you push to smaller scales in the lensing. So this is now the angular scale of the lensing map itself. SPT and the combination of SPT and Planck really measure these smaller angular scales well, whereas the noise is kind of blowing up here in the Planck map. So because Planck gets the whole sky, they have just an exquisite measurement of the lensing power spectrum. The best in the field by far. This is amazing, a single precision of around 2%. In the SPT maps, these maps are significantly lower noise, but because we only cover 2,500 square degrees, we will not measure the power spectrum to these levels. But with these deep maps, they're very useful for cross correlations as well. So this is the power spectrum of our lensing map, shown here, function of angular scale. And so we find constrain this to a lambda CDM plus a lens model, and we find an amplitude for the lensing power spectrum that's consistent with the expectation. 1 would be the expectation for lambda CDM. So this is still a pretty precise measurement of the lensing power spectrum, whereas the Planck spectrum had a statistical precision of 2%. This has a statistical precision of around 6%. And then this rejects the no lensing hypothesis very significantly. The reason this is 24 is not 95/6 is because for the no lensing hypothesis, you have less. That would be if the universe is unlensed. What's the probability of getting distribution like this, and so you don't expect things to fluctuate as much in an anomalous universe. And so we've something to point out for thinking about the future. We've kind of highlighted this high L part of the lensing power spectrum because we're starting to see an upturn here, which we believe is contamination from foregrounds. So this is actually what set the high L cutoff of what we thought was uncontaminated and able to use. But this, this is an area of pushing right now and of working forward in the future. And then we show our systematics tests over here, and they are consistent with 0.
So the A lens is for the coax, right?
A lens is for SPT plus the reconstruction from the coax.
Do you happen to know what it is for SPT only?
It's I have to look up the exact number. I know this doesn't change. The statistical error is exactly the same, and I forget if this is 0.96 or 0.94.
Which is interesting because of consistency, right? You're kind of
right. Yeah, we don't see any big changes there at all, and the let me get to this. So key takeaway points from this combination are that the SPT information dominates at small scales, Planck at large scales, obviously. The lensing power spectrum is dominated by the SPT information at few arc-minute scales. So this is what Blake was saying. The statistical precision of how well we measure the power spectrum actually isn't even changed at all by adding Planck. So you might say, like, okay, well, why did you even go through all this effort? But this large-scale information from Planck, in this quadratic estimator, you're looking at the correlation between modes. So if you fill in these large wavelength modes, it actually really helps out here at the small angular scales of the power spectrum, which is particularly important for cross correlations. And you can understand that as if you're trying to build triangles in harmonic space, if you measure some of these long wavelength modes, then there's you get basically access to a lot of smaller wavelength modes that weren't measured before. So adding in this Planck information, that actually helps a lot for building really deep maps and for the cross-correlation science that we hope to do. So because one of the main purposes of this map is now cross-correlations, we took the cross-correlation with the cosmic infrared background, where we use the Planck 545 gigahertz map. And here we're showing an overlay of the two. So the color scale is the CIB, and the gray scale is the CMB map. And you just even see by eye that they line up incredibly well. This is not new, but it's showing that it works. This is now the cross-correlation spectrum of these two maps, fitted to the Hollow model, and then showing in the squares the similar measurement from Planck over the full stack. And then last thing about this measurement, this map has extremely good coverage with the dark energy survey. So in orange, this is showing the dark energy survey region, and blue is showing our 2500 square degree region, and then this is showing the exact overlap. So in dark gray here, this was the science verification field from the dark energy survey. In lighter gray is the first year of data, year 1 from DES. And we have, we have very good coverage, something around 1300 square degrees. And especially, I mentioned those summer fields, there's even more coverage with those summer fields as well. So these are all ongoing analyses of cross-correlating this lensing map with galaxies, shear, clusters, other data products from the dark energy survey. Good, so takeaway points from this measurement. So why this measurement matters. This is a precise measurement of lensing power spectrum, so it's cosmologically interesting, and we are working on those implications for cosmology right now. It's a signal-dominated map that will be quite powerful for cross-correlations, especially with the dark energy survey, and it provides excellent coverage with DES. And so this will be the primary map for cross-correlations with DES until we have a similar map from SPT3G. Okay, so moving on to the second analysis. We're now talking about no time. Okay. Why don't let me just flip to the maps. So we've also run a reconstruction analysis on SPTpol. This is not published yet. We're getting closer. So these are maps from that analysis. And minimum, so as I mentioned, the quadratic estimator you can combine T, E, and B. So this is the minimum variance maps, or our best estimate of including all of that information. Still heavily dominated by temperature at this point. But we're actually now getting a significant measurement from the EB estimator, which is pretty cool. So this is one of the estimators that for the future is going to be very powerful, since it's for one reason, it's much less sensitive to foregrounds because it's based on the correlation information. And actually, we're getting a similar statistical significance here to the 2500D survey, but even only on 500 square degrees. So these are really powerful maps. So I guess since I'm out of time, we found a cosmic duck, which is which is fun. And high stable noise maps. What this is what those error bars will look like. It'll lead to 5 to 6% precision on this power spectrum, and then comparing to the rest of the field, ACT and Planck around here. And key takeaways from this are: this is another precise measurement. We've significantly measured the polarization in EB. So this we're also working on cosmological constraints, and then this has direct overlap with bicep CAC for D1s and more. So with that, I will stop.